Hi everyone, welcome to the video recording talking about a recent research paper that EdgeBit published around enforcing SBOMs and providing workload integrity based on the contents of an SBOM. I'm joined here by Alex and Eugene, two of the co-authors of this paper, and we want to talk you through some of the specifics of it. In case you don't like reading it in paper form, we're going to talk about it here. Welcome Alex, welcome Eugene, thanks.
Thanks, Rob.
Great to be here.
So I'll tell the listeners a little bit about this paper, and then I'll ask you guys some questions to dig in more. But we set out a few months ago to answer the hypothesis of, is it possible to go beyond, signature validation and kind of what we typically do for container workload startup? And can we enforce the contents of a container, of a workload, to match an SBOM 24/7? Today's EdgeBit security platform, we can consume SBOMs, we can process them to understand risk, and we use runtime context to remove the noise inside of that risk determination. But what we can't do is be sure that the SBOM is the absolute perfect proxy for that risk, because we don't have a way to enforce that the workload hasn't changed after it's been running. So that was the research paper that an effort that we set out to do. Make sure that the workload remains faithful to its SBOM. This paper we presented at the Software Supply Chain Offensive Research and Ecosystem Defenses event, SCORED, as part of an ACM event in Copenhagen. And so in case you missed it, we wanted to talk through this paper and cover some of the major topics today. One of the original motivations for this paper is around environmental threats. This is when your application is actually running. So that means the state of the running server, the workloads. And I'll put up a modified version of the SALSA threat diagram that adds environmental threats to this. We think this is really important. Alex, can you tell us a little bit more about why this is so important?
Yeah, Rob. I think it reflects kind of the changing environment when it comes to software development and deployment these days, both in terms of the complexity of the software, but also in terms of the complexity of these attacks. So if you look historically at how attacks are done on software services, we have shored up a lot of our defenses by using better languages, better tooling. We look at things like Valgrind, decades ago, had helped remove a whole class of vulnerabilities, and now we have this strong push for using memory-safe languages. So the bar to clear for attacking these systems is quite a bit higher, and just the economics of it have allowed attackers to, I think, explore different avenues for getting into these systems, and that includes the entire supply chain as well. So when we consider how do we make sure that a software service is secure, not only do we need to look at the executable, but we need to look at the entire process for creating that executable, the people involved, all of the tools and software. And as anyone knows in this industry, this is a substantial attack surface that needs to be considered. And so we're trying to expand a little bit in terms of exactly which parts of that attack surface we're trying to protect.
Awesome. Yeah, absolutely makes sense. It's a vast attack surface, unfortunately. And the paper breaks down the process of how we went about researching this. So there's a number of different pros and cons for different technologies that we can use to do this type of enforcement of an SBOM. Eugene, I was wondering if you could tell us like the constraints that we're working under, because while this was an academic paper, kind of getting something that's widely used in an enterprise has a bunch of different constraints that are maybe a little bit more technical than just doing some research. Eugene, can you tell us about that?
Sure, Rob. Yes, definitely the constraints were a big part of this effort. Like you said, this was a research paper, but ultimately our goal is to get it into the hands of the enterprises. And those enterprises require the most frictionless experience of getting it into the hands of the engineering, into the production. And so the number one constraint that we were working under was the ease of installation. So this kind of ruled out the use of kernel modules because they're hard to both install and then upgrade, and also things like rebooting the server, which are not that convenient to do in a cloud environment. We also wanted to work with all the popular Linux distributions, especially the ones that are powering the Kubernetes workloads, such as the Google optimized OS. And if you're deploying this in in the Kubernetes environment, it should be as easy as just dropping a daemon set and then let it cover the whole cluster environment. Also, for those enterprises that are still using RPMs or jars, we also wanted to work under those environments as well.
Awesome. Yeah, and as you'll find out, this kind of shapes everything that we talked about. So let's dig into some of the technologies that we ended up looking at. Some of them we discarded. And so the first one, Alex, is about the integrity measurement architecture, or IMA, that's built into some of the modern Linux kernels. Can you tell us about that?
Yeah, sure. IMA is a subsystem within the kernel that more or less measures the contents of a file when it's accessed. So whenever you go to read a configuration file or read an executable, the kernel in a very performant manner will more or less generate a digest of the content and then compare that against some known good values. And you can provide a policy, an IMA policy to the kernel, and that will more or less control which files are subject to these rules. But also there's a certain amount of flexibility in how you mark whether a file is okay to be opened or not. And that can be done as a digest, that can be done as a signature. But all of this information is stored within the file system and within the extended attributes of those files. So as long as you're able to ensure that these security extended attributes haven't been modified, you can then be guaranteed that the contents of these files similarly have not been modified.
I think you started to lay out some pros and cons for IMA. Can you just list those really quickly for us?
Yeah, so under the pros, IMA is very performant. It is built into the kernel. Not all kernels have it enabled, but it is fairly common. So I think for the most part, you can depend on that. It also can operate in two different modes. You can strictly enforce the validity of these configurations, but you can also just fall back and audit, which means that you allow these things to happen, but then you can check after the fact and say, oh, we see that the file was accessed, but it had been tampered with. In terms of the cons, it is a little bit more restrictive in the policies that you can describe because you're limited to signatures and digests. It really doesn't provide a mechanism for applying to dynamic files like etc resolve, for example. This works really well for stat files, for executables, for static configuration, for things that you know up front. But for things that are being modified, it's a little bit more difficult to express some of these policies.
Yeah, I think one of the issues too is it's not really tamper resistant on its own, which comes to our next piece of technology, which is the extended verification module, or EVM, which is pretty closely associated with IMA. Can you tell us about that really quick?
Yeah, so I touched on this slightly just a second ago, and that is the signature or the digest for these files is stored within the file system extended attributes. So you can imagine if an attacker is able to modify the lower level inodes, or even just modify the extended attributes on these files, they can potentially just add their own signature or add their own digest to get around the whole mechanism. So you need a mechanism for protecting this metadata, and that's where EVM comes into play. So EVM works pretty similar to IMA, but instead of looking at file contents, it looks at file system metadata. So it will look at the security extended attributes, and that is much less granular. That's just an on switch. In fact, there is no off switch. As soon as you flip it on, it's on until you shut down the kernel, and that's typically you would pair these two mechanisms together. You would have IMA protecting the contents of the files themselves, keeping that metadata, keeping that security information within the metadata, and then you would have your EVM, which protects that file system metadata from further tampering. So the combination of these two can ensure that nothing in the file system is being modified at runtime.
Awesome. And we'll throw up a few kind of the sample commands. You mentioned doing this kind of dynamically and at scale. Here's some of the CLI commands you could run to just do this manually. Of course, you would want to automate this. And so just like IMA, EVM has some downsides, some pros and some cons. Can you tell us about those?
Yeah, similar to IMA, it is very performant, and it's a great tool for preventing malicious tampering. Major downside though, a lot of kernels don't actually get built with the EVM enabled. The last I looked, which was a couple months ago, both Amazon Linux and Google's Cloud Optimized OS don't come with EVM enabled. And there are good technical reasons for this. This is not simply an oversight. This is just there's a lot of extra machinery that needs to be in place for these things to actually be useful. But it's something to keep in mind if you are going to be experimenting with this sort of stuff. You're going to run into a little trouble right off the bat, and you're probably going to have to use your own kernel image.
Yeah, that seems like a pretty big blocker. And, our research paper kind of talks about this as well as tended to kind of stop here. All right, let's see what else we can have in our toolbox. And we already use some similar technologies in EdgeBit's platform today, eBPF and Linux security modules. Eugene, can you tell us about this kind of leg of the research?
Sure. So eBPF is a relatively modern technology, but at the same time, it's fairly well supported by the distributions. And so the way it works is that a user space process can inject some code into the kernel, in some sense similar to a Linux kernel module, but this does not require, it's not as invasive as a kernel module. And so the kernel then verifies the eBPF code, and then it's able to hook into the Linux kernel in certain spots where it's necessary. And so one of the spots where we can hook into is called the LSM, and these are the set of hooks that security modules such as SE Linux and AppArmor use to make a decision at whether or not a certain operation is going to be allowed. And so this gives us a way to do some verification and prevention to make sure that things like extended attributes that contain these IMA hashes are not being removed by the attacker.
Awesome. And we'll show an example eBPF program up on the screen so folks can get a sense of what this does. But these are relatively simple, is that correct? But the way you use them and layer them together is what makes them so powerful.
Yeah, so a single eBPF hook is typically just a couple of lines of C code that looks at the parameters and makes a decision whether or not to allow the code to proceed, and then it's able to just return a zero if it's all good to go, or an error code saying that in this case, like a permission is denied for this operation.
So this is pretty promising, and it's really cool that these programs are so simple. So there's a lot of pros here, but also some cons. Eugene, can you tell us about those?
Sure. Some of the problems is that there are certain restrictions that are placed on the eBPF programs. For example, they can't call into arbitrary Linux kernel functions. And so this restricts things like calling into the virtual file system sublayer of the Linux kernel to get some of the more deeper information about the inodes. And so we ran into a problem where we would need to, before making a decision on whether or not to allow the system call to proceed, we would need to read out the information out of an inode, and that's something that's currently not really possible with eBPF.
Gotcha. Yeah, that was a little bit of a bummer, but eBPF has a lot of pros going for it as well. Can you tell us about that?
Sure. I mean, the biggest advantage is the ease of deployment. This technology really took off because deploying it as easy as creating a user space program, putting some bytecode in it, and then at runtime, a single call to inject it into the Linux. So the deployment story here is just beautiful.
Gotcha. So I think that really fits all of the requirements that we laid out in the beginning. No reboots, works with most Linux distros out there. Very easy to install in both containerized, non-containerized, Kubernetes, no Kubernetes. So that seems great. Um, Now, I understand for this scheme to work, since we're embedding some metadata into the file system, we need to change kind of the build pipeline, understand what dependencies are in our app, but then kind of tell the system about that. Alex, can you explain kind of what happens in a build pipeline now to implement this scheme?
Sure. Yeah, so as for implementing the scheme itself, that involves writing more or less the extended attributes to the files. We can use tools like EVM CPL to create these signatures or digests. And then fortunately within a container image, because the files are just tarballs, all of the file system metadata, including the security extended attributes, come along for the ride. So once you build your container image, it actually has all of the information in there that is needed by the kernel to determine whether or not any tampering has happened after the fact. Now, in terms of understanding the dependencies that went into that image, the industry standard is to generate an SBOM, or a software bill of materials. And there are a number of tools for doing that, but more or less, these tools will scan through all of your dependencies in code and list those in an SBOM that can then be later analyzed by vulnerability scanners. But more or less, this SBOM acts as a surrogate for the contents of this image. If we're able to know that this SBOM does in fact represent what was in that image, like you were mentioning before, then any analysis we do on that SBOM is then valid for that running application.
Awesome, that's good news. So it makes it pretty easy to implement. And as you said, this is just kind of part of the file system. So this goes along for the ride, as you said. So that works with like most container registries out there. And so it's just throw it on a kube cluster and you're good to go.
Yeah, exactly. Yep. Most of the container registries, at least the ones that I tested, were perfectly compatible with this scheme.
Awesome. Yeah. So that hits our kind of frictionless ease of use on the build side as well, which is great. So when you zoom out, you can see where our build pipeline fits into this entire flow from code to deployment. And in this diagram, you can see at the top, this attestation is being generated. I like to say that attestations put kind of the chain and supply chain, if you will. And so, Alex, can you tell us about the Salsa framework, code provenance, and then how this in toto attestation kind of fits together to chain this trust?
Yeah. So all of these mechanisms, more or less, are driving toward provenance for your build artifacts, knowing how they were built, knowing what went into them. And we'll start with Salsa. So Salsa is a mental framework for classifying the level of trustworthiness of these different systems. The Salsa 1.0 spec right now is focused on builders. So you'll see the Salsa security levels defined as builder L1, L2, and L3. And more or less, these are just ratcheting up the amount of trust that you have in the authenticity of the artifacts that come out of this build system. Build L3 being the highest level, you have a very hardened builder. You have a high degree of confidence in what comes out of that build pipeline. And then in toto is this emerging industry standard that is more or less an implementation of the Salsa framework. So within in toto, there's a number of different attestations which are defined. And so as you build these different pieces of your application, you generate these different attestations. These all can chain together into these bundles. And from that, you're then able to derive after the fact the ultimate provenance for your build artifact.
And these like links, I'll call them in the chain. This is like I ran a Go builder with these types of flags against this GitHub checkout that came from here. I transformed it in this way. I generated this SBOM, that type of stuff.
Exactly. Yeah, it's more or less a proof of the steps that went into going from source, and actually in some cases including the source, but going from source to the ultimate artifact.
Gotcha. And again, that's key for this because if we can't trust it all the way through, we want, to verify the integrity of this SBOM and then enforce it on the file system.
Exactly.
So very key to this whole thing. All right, and Eugene, the paper kind of concludes that, as we talked about, there's some gaps in the Linux kernel for us to be able to do this. Can you tell us about those? I think it was some eBPF stuff, some IMA stuff. Tell us about that.
Yeah, for eBPF specifically, the only compatibility issue that we have is with older systems like Rails 7 that might run into issues, since it's pretty well supported across the modern distros. But like we mentioned with EVM, the huge blocker is the availability of it and how it's not enabled in all the kernels that we need. So we want to use the eBPF technology where possible. However, that runs into the lack of capabilities to deeper inspect the kernel structures, being able to call into arbitrary kernel functions to get the data that we need before making the decision in the LSM hook.
Gotcha. So yeah, our paper kind of concludes that ultimately that LSM hook side of it is really the main blocker for this, and we hope to kind of drive some of that forward or explore more workarounds to get to this kind of end-to-end verified and enforced SBOM state. So again, you can read the paper. If you didn't get enough information, there's a little bit more, as well as a blog post on edgebit.io outlining kind of our motivations for this, both academically and commercially. And so we thank you for joining us today. Hope we find this topic interesting. Please reach out if you are interested in this type of tech, or if you think this could help solve problems at your enterprise and inside your security engineering group. We would love to chat. As we said, there's a lot more work to be done here, and we're doing some other interesting work on pushing the boundaries. The great news is if you're building SBOMs and you want to do risk analysis, you can do this today and be very successful with it. The EdgeBit security platform understands SBOMs and producing risk, associating those with running workloads, and then doing prioritization of the vulnerabilities found, understanding which parts of your application are actually active and which parts are dormant, and that helps your security team tackle the right vulnerabilities at the right time. So reach out if that is interesting to you, and we'd love to hear from you. Thank you for joining us today.